All right, welcome to the fourth section of the Algebra 2 summer packet at Richard Montgomery High School, and we are going to be doing 25 through 32 with you right now. Thanks for hanging with us, and hopefully after this review, if you'll feel very prepared for your upcoming Algebra 2 course this year. We're looking at this in this first section of problems here. We're looking at lines in particular, and we want to think of lines as having a y-intercept and a slope in particular on number 25. So what is the slope of the line that passes through both of these points? So you could draw this out and maybe count some blocks. And remember, we think of, there are a couple cute ways of thinking about the slope. We usually refer, at least in the United States, to the slope as being m. Not sure why exactly, but do you know why?
I think it's for movement.
Movement. All right, there you go.
Movement along a diagonal line.
And there are a couple ways you can write it. So some people kind of say cutely, rise over run. Or sometimes people say change, actually write out the words change in y over change in x. Or you could say vertical change. There are lots of ways you could say this. Over horizontal change or whatever. There are lots, because it's such an important idea. You could say change in the output as a result of the change of the input down below or something. Or sometimes people just say change in y over change in x using the Greek uppercase letter delta. And the change in y and the change in x can be computed if we have, we might call this x1 and y1 and this x2 and y2, the coordinates up here. Hopefully you're used to thinking of those in that order, x comma y, x comma y. And the change in y would just be the difference between these y coordinates. So you might do y2 minus y1 over x2 minus x1. So here that gives, and I would just caution, I mean that's a nice formula, you can just run with it, but be real careful because it's easy to say this and then not do it because because you mix up, you put the x's on top and the y's on the bottom by accident, or you do 9 minus 5 up here, and then down on the bottom you do 6 minus 3 instead of 3 minus 6. Whatever. As long as you're careful, you will get this right, and you might even want to label these x1, y1, x2, y2 in order to make sure there's no mistake made. So there's our final answer, negative 4/3. If you needed to simplify this fraction, that would be a wonderful thing to do. And then one other note too. Some people are like, well, which one is x1, y1, and which one's x2, y2? And actually, my choice is arbitrary. Does it work if you do it the other way? Just to maybe you've thought about this, but just to remind you, can you do it the other way as long as you're consistent? The answer is yes. So here you get negative 4, and down here you get 3, and of course negative 4/3 and negative 4/3, those are the same. It doesn't matter where the negative is up on the top or the bottom. So either way works.
All right, I'm going to do the next one, finding the x-intercept and the y-intercept. And it might be helpful if you remember, a definition of an intercept is the other thing, if you will, is 0. So I say to myself, if I'm looking for an x-intercept, I'm looking for an x value when the other value, y, is 0. And if I'm looking for a y-intercept, I am looking for when a y value when x is 0. So those two things just kind of happen in my head. You don't have to write it down, but I think it's helpful because when I realize that I'm looking for the point x comma 0, and then I look at this equation over here, well, if I want to know when y is 0, just go to this equation and make y 0. See what you want and make it happen. And I love multiplying by 0 because bye-bye, that goes away. And then I'm just left with negative 48 still on the right, but only 3x. Divide both sides by 3. And usually that is negative, what? 16. Yes? So what does this tell me? When I made y 0, x was negative 16. So I can go over here and say the x-intercept is indeed negative 16 when y was 0. I can do the exact same thing, thinking process for the y-intercept. So I'm going to go over here, I'm going to get rid of this work. Thank you very much, all done with you. And I'm going to repeat the process just with the other variable. So I want to know what y I get when x is 0. So I'm going to go to the equation. I'm going to replace x with 0. Love multiplying by 0 because bye. Negative 4y is equal to negative 48. Divide both sides by negative 4. And shockingly, negative divided by a negative is not a negative, right? Negative divided by a negative is positive. And 4 goes into 48, a nice integer value of 12. What does that tell me? Again, over here, when I put 0 in for x, I got 12 for my y value. So this says to me, and often, intercepts are critical values of any function. I want to know where my function hits the x-axis, where does my function hit the y-axis. And if I ever did need to graph this, some people are so married to one particular form, but graphing from intercept form, all you need is 2 points to get a line. I can plot this point, I can plot this point, and I would have my line. And I would be able to calculate a slope from that. This is a perfectly viable equation of it, just not in slope-intercept form, but that's all right.
All right, and then this number 27 is fairly straightforward if you remember even a little bit some of our famous forms of the equation of the line. This sketch just showed you standard form. This is called slope-intercept form. Maybe you remember that. And m, remember I talked about up here, is the slope. And b, again, not sure why, but
Don't have a good,
except sometimes this is ax plus b,
right,
in which case that makes sense. All right. All of it's arbitrary. It's a thing.
Yes, it's a thing.
And we could explain why this works, but if you remember that form of the equation, it's a wonderful form of the equation, then our work here is done.
Yes.
3/5 x. And what's the y-intercept? Negative 4. And I'll move on without any more commentary.
Although if you wouldn't see the link between this problem and the problem number 26, surely if, again, I'm looking for an x-intercept, what are you going to do with Mr. Chase's equation? But you're going to plug in that 0 for x, and 3/5 times 0 is gone. And then y is equal to negative 4 when x was 0, which is why this is, pun intended,
Yeah, we should.
the slope y-intercept form.
Yeah, we should never lose sight of like what y-intercept means. It's the value of y when x is 0. Yeah, absolutely.
Next, 28, find the equation of a line. Notice that they said, find the equation of the line. They did not dictate to me which form to put the line in. So that gives me some freedom, which means I can write the equation of a line in any way I choose, and what would be the most efficient way for me to do it with the least amount of places for me to make computational errors, because we all do that, especially in a testing situation. The point-slope form of a line is the most convenient given 2 points. And the point-slope form of a line looks like this, where I have a y minus a y-coordinate, so I'm going to leave a blank there, is equal to the slope times x minus an x-coordinate. So I'm going to leave a blank there. So x1 goes here, the slope goes here, and y1. And you might ask, well, what is x1 and y1? It's any point on the line, hence the convenience of this form, because they have given me 2 points. 1, 2. I could use either one of those. It does not matter. So I choose, just because it was given to me first, the point 1, 2, and I'm going to put the x with the x and the y with the y. And now to get the slope, I have to use something that Mr. Chase did in the previous slide. I have 2 points, and I need to calculate the slope. So the slope is a ratio of the vertical change. So if I think of this as x1, y1, x2, y2, then I have negative 4 change 2. I have 3 change 1. A common error for that numerator is to say that that is negative 2. But remember, you have negative 4 minus 2, which is a negative 6. 3 minus 1 is a 2. And you might even try to picture that. If I'm at -4 and I had to walk to a position of 2, well, I have to walk 4 steps to get to 0 and then 2 more steps to get to the value of 2. So I have -6/2, which of course reduces nicely to -3. Since I just found the slope, take the value -3 and put it in the slope position. And leave that equation alone. Unless somebody makes you distribute, combine, get y equals mx plus b, find the y-intercept, please do not. That is a waste of time on an assessment, and oftentimes in these higher level math courses you are struggling to finish in a test in the time allotted. And this is one thing that can save you maybe just a couple seconds, but over time those couple seconds end up to be a couple of minutes at the end of an assessment.
Yeah, and both Ms. Getz and I, Mr. Chase, teach calculus, and we won't tell you why maybe yet, but we will tell you that this is maybe the most important form of the equation of line for us.
And the most convenient for sure.
So it might seem weird now, but you'll thank us later.
Yes, you will.
Find an equation of a line that passes through a point parallel to a given line. Awesome. The thing you need to know about parallel lines is that they have, is this too much of a spoiler alert? They have the same slope. Let's just get it out right now. If you were to, you could play around with this and show that this is true. It's clear once you draw a picture maybe. So that being said, what is the slope? Can you see it from just looking at this line? There it is, right? That's our m value. Wonderful. So m is 3, and we have a point. Again, does it say, right, which form of the equation we want? So I'm going to pull a Miss Getz on this, and I'm just going to use the point slope form. So y minus our y coordinate equals the slope, which we've decided because they're parallel is the same as the slope of this line, 3, times x minus -1, or how about x plus 1 would be maybe the slick way to write that. If you want to rearrange this equation, feel free. But you can also leave it that way. If it says find an equation, there's one.
And similarly for number 30, the only thing notice that they changed here was from Mr. Chase's parallel, they're giving me perpendicular. So while the relationship between parallel lines and slopes is that parallel lines have the same slope, perpendicular lines have slopes, and you can think of this a couple different ways. You can think the negative reciprocal, or you can think the product of the slopes of perpendicular lines is equal to -1. I kind of like to say take the slope, negatize, and flip, but negatize isn't a real word. Mr. Chase doesn't like that, but I do. So
Negate is a perfectly good word.
It is. Find an equation. So again, that allows me to pick the one that is the most convenient. They've given me a point. That point is not the y-intercept, so why would I go to slope y-intercept form? I will just...
It's supposed to be y equals down there, huh?
Yeah, oh, that's right. This is a typo here, huh? This should be y equals x plus 2. So the first thing I have to do is look again for the slope on the line that is given to me. The slope is a +1. Therefore, the slope of the perpendicular would be the reciprocal of 1, which is shockingly still 1, but negatize it. So -1, so I'm going to say y minus my y value, which is -5. So again, I'm going to make that y plus 5 is equal to my perpendicular slope, -1, which I can just write like this. I don't have to write the 1, or I can. And I can say that that is x minus -2. And again, go ahead. This would certainly not be difficult to distribute the negative through and whatever. That would be perfectly fine, but I just don't have to.
Be as lazy as possible.
That's right.
That's what I say.
I like to say efficient, Mr.
Efficient,
Chase.
excuse me. Yeah, all right. All right, so I'm going to do all 3 of these just because they're boring. I didn't say, I mean, they're exciting is what I mean. But all they want you to do is to compute the value of y, given a certain value of x. Now, the interesting thing is this deals with, like, up here we have something called a quadratic, down here we have something called a cubic, and down here we have another quadratic. So, I mean, that makes it slightly more interesting. All right, so let's take a look at this first one here. If we plug in 4, I think maybe the takeaway from this is going to be, are you good at order of operations, and do you know what it means to square things? Now, one could just hand this to the calculator, but we'd like to be able to do this without a calculator. So 4 squared, remember by 4 squared would mean 4 times 4, which is 16. And that's the thing you should do first. And then 3 times 16 is 48 minus 5 is 43. Is our answer there. That's what y is. Down here, again, we need to think about how to resolve the cubed power. And also, maybe, what is that? Yeah, maybe let's do that off to the side here. What is negative 3 cubed? By definition, it means negative 3 times negative 3 times negative 3. So common mistake would be to maybe say 9 here, because 3 times 3, but of course this is not 9. This is negative 3 times negative 3 is positive 9. Times negative 3 is negative 27. So 4 times negative 27 plus 1. Now, so notice that when you cube something, you can get a negative number. That's not a problem for us. That doesn't happen when we're squaring things. We can generalize that principle if we wanted. What is 4 times 27? I don't know. Let's see. I know 4 times 30 is 120. So this must be 12 less than that. So what is that, 118?
118,
All right.
I believe, but negatized.
But negatized, excuse me. So I'm going to go with negative 117. People with calculators somewhere can check me on that, but I think we're good. And down here, I like the fact that we're thinking about function notation down here too. So that's cool. Plug in 2. Just to remind you that we can think of all of these as being like inputs and outputs, and this really emphasizes that. This one I like too, because we have to be really careful about this negative out front. I think this is a pretty common mistake. People think, and look, we have to plug 2 into 2 places as well. That's kind of fun. Sometimes people read this as being, I emphasize this with the parentheses because we're going to resolve this power first, and then we're going to make it negative. It's like there's a negative 1 out front here. I think this is very common that people think, oh, negative 2 squared, that's positive 4. But wait, here we're doing 2 squared, and then only afterwards thinking of that as being negative. So that'd be negative 4 minus 28 is negative 32. All right.
I do think, Mr. Chase, that negative 27 times 4 is negative 108 maybe?
Oh, 108. What did I say? 120 minus 12.
Yeah.
108. All right. Good. That makes us human. Perfect.
Yes.
All right. Moving smartly along.
All right, so the next problem, number 32, has lots and lots of problems. And this is the part where we just really need to make sure you have these skills. And I know you learned the skills in Algebra 1, and I hope that your algebra teacher emphasized writing out, making sure you are combining and collecting at the right times and multiplying correctly and writing each step out. There is a purpose to doing that, and it's to try to get you to recognize patterns. So here by Algebra 2, our hope is that some of this stuff begins to be mental. And you don't need to write down each of the Algebra 1 steps because there's going to be more Algebra 2 steps in each problem. And of course that leads to pre-cal and to calculus. It all does build on itself. Every calculus problem starts with Algebra 1, then has some Algebra 2, probably has some pre-cal trig in it, and then you get to the calculus. So if you have to write out every single step along the way, again, that's going to hinder your time and your performance on some of these high-stakes tests, be they exams, AP exams, tests in class. So when I'm doing a combination here, I'm not solving for anything. There's no equal sign. I'm not solving anything here. I'm just doing a rewrite, kind of like when you rewrite 10 plus 5 to be 15. I am writing something plus something else, and I'm going to try to write it in just a more convenient form. So the first thing I have to do is say, well, who matches up? So I have a squareds here, and I have a squareds here. I notice that because it's a plus here, if you were to think about distributing a positive 1 through all of these, there would be no change to the negative 7, the positive 8, or the positive 2a squared. So combining like terms here, if I have negative 3 of these and 2 more of these, well, I have negative 1 of them left. Then I have a to the first. I have positive 4 there, and I have negative 7 there. So that's negative. You have 4, you lose 7, you're 3 in the hole. Now I have negative 7, a constant, and positive 8, another constant. They match up. And if I have negative 7 but then I get 8, well, I am 1 to the good. And that's it. It is usually nice to have polynomial expressions with the highest exponent first, and then in decreasing order. Technically, you can think of this as also having an a, right? An a to the 0, if you will. We usually just don't write that, like we don't write this exponent of 1 either, although we understand that it is there. So the trick with the next one is to realize human beings make more mistakes, mental mistakes, not stupidity mistakes, just computational mistakes when they subtract. We make more when we subtract than when we add. And one of the things to be careful about is to make sure I am subtracting everybody here. So you can think of that as distributing the negative. So the 13 will be negative, the 3x cubed will be negative, the 2x squared will be positive. The negative x will turn to a positive x, and the positive 8 will turn to a negative 8. So I'm just going to kind of do this. I'm going to change this to a plus, so I say to myself and, but I'm going to negatize everybody inside that parentheses. And now I'm going to do the same process I did before. I say, well, I've got 39x to the 4th over there, and I'm going to take away 13x to the 4th. So how many x to the 4th do I have left? 39, take away 13 is usually what, 26? Am I right there? Today. Today being Tuesday? Or Wednesday? Oh, Wednesday. So Wednesday it's the 26th. JK. Let's see, what do I have with my x cubes? I have minus 4x cubes there, and another minus 3x cubes. So that's minus 7x cubes. Here's my x squared, so I got positive 2 of them, and a positive 2 more of them, which is 4x squareds. I have a negative x here, and a positive x there, but there are no x's left. And of course I could write 0 x's, but I choose not to. And then lastly, I have a negative 7 for a constant and a negative 8 for another constant. Negative 7 and negative 8 is negative 15, at least on Wednesdays.
We could use this opportunity to say something about terminology too. These are both polynomials, and
yep.
This is called a trinomial. This is called a fourthy, a quadnomial. I don't know, because it has 4 things, 4 monomial terms. This is a fourth degree polynomial, and this is a 2nd degree polynomial. Something that we'll learn lots more how to classify and graph and how they look in Algebra 2. But we can start using the technical language now. All right, we get to multiply now. This is fun. I think that, if you've done Algebra 1, maybe you remember, or even in pre-algebra maybe, the idea of like foiling, F-O-I-L. And that's kind of a cute acronym. We use that to stand for first, outside, inside, last, which helps us just do some bookkeeping on this multiplication. So let's do that. But I also want to maybe make a few comments about why that's a little bit of a black box to some students too. I want to make sure you understand why that works. So if we do that, let's be careful. Y times y, this didn't happen on the previous 2 problems. Y times y, that's not 2y, that's y squared. That's like if you were multiplying 2 times 2, be 2 squared, be 4. That's a bad example. 3 times 3 is 9, right? It's not 6. Plus, we'll follow it religiously in this order. Those were the first. Now we're going to do the outside. These 2 here. Negative 3 times y. If I have negative 3 apples, I have negative 3y here. First, outside. Inside, we're going to do next. Plus 7y. 7 times y. And then last, we have 7 times negative 3, which is negative 21. Cool. And then often what we can do, not always, but often we can combine these middle terms. And that would be the simplest way to write that. We've combined the things we can combine. We can't add y squared and 4y together. They're not like terms because they don't have the same variable part. But then just, again, another word on why this actually works. Like, some students might be like, well, what if I do F-I-O-L? Is that okay? Well, absolutely. Yeah, there's no reason you can do these in letters in any order. That's for sure. And just a word, again, maybe why this works, because when we get down to this one down here, for instance, we're going to need, like,
Foil doesn't work,
Superfoil or something,
Yeah.
right? And, like, let's stop making acronyms then. Let's, like, just think about reason it through why this works. So, you know how to do this, right? That's just a times y minus 3a. You're just distributing. It's called the distributive law. Well, that's actually what we're doing here, too. We have something. It's, instead of an a, it's a y plus 7 times y minus 3. So the same principle applies. I'm just going to do the same thing up here. I'm going to do y plus 7 times y minus 3 times y plus 7. You see that all I did is replace up here the a's by y plus 7. Is this the same thing we have down there? Let's keep going and see. Here we get y squared plus 7y if we distribute from the right. And over here, what do we have? Minus 3y minus 21. Is that the same thing? Looks like it. If we combine these two terms, we get the same result. So I'm not going to do that for the other ones. I'll do it more quickly. But I just want to emphasize like why the principle behind why this works. This is just kind of super distribution. It's not any special rule like, oh, in this situation we need to like FOIL. This is like a different thing than before. No, it's the same thing.
And if nothing else, just try to increase your speed with these kinds of problems.
Yeah.
Can you get to y squared plus 4y minus 21 in your head?
Yeah, and maybe let's do that on this one because something kind of fun and nice happens, right? So let's do that. X squared, we're getting good at this. We've always seems like we get x times x is x squared. If we do outside, that's negative 12x. I'm just going to catalog that in my head though. And then on the inside, we get a positive 12x, negative 12x plus positive 12x. Let me get out my calculator. Oh yeah, that's right. That's 0x. If we add negative 12x and positive 12x, that's 0. And then 12 times negative 12 is negative 144. So yeah, we'll try and do like Ms. Sketch just said. Let's see if we can get these a little more quickly so that we can move on to automaticity as we move into algebra 2 here. P times 3p, a little trickier because we got a coefficient on the second p, is 3p squared. And then outside is 2p, and the inside is negative 6p. Are you following? 2p and negative 6p is negative 4p. And then the last would be negative 4. So yeah, we're going to try and quicken this up. The process is the same on all of these, but we're throwing little different things at you. Here the middle terms canceled out. That was cool. Here we've got a 3 there. Down here we've got, is this the same situation? Actually, yeah, it is. Common mistake would be to be like, okay, 6m, I know that's 36m squared. And negative 5 squared, I know that's 25. Got it.
This is such a dagger.
Nailed it.
Right.
No, you didn't.
No, you didn't.
Fail. Isn't that what the kids say these
I
days?
think so.
Fail.
We're so hip, Mr. Chase.
We are. Okay. So 6m minus 5, let's remember what the definition of what it means to square something is. Times 6m minus 5. You will get a 36m squared, and you will get a 25, but you know if we've done this with us on the previous problems, then you get some other thing as well. We get 36m squared. What's that middle term? We actually have one, don't we? We get negative 30m and another negative 30m, and that always happens. We're going to get twice negative 30m, so that's negative 60m. And then we do have that plus 25. That's negative 5 times negative 5. And we want to recognize some of these forms because in a few problems we're going to be doing some factoring.
We're just going backwards from this.
Yeah, and it's going to be really helpful to kind of like think about this forward process and in order to do the backwards engineering. This one should remind you a little bit of the form of D up here. It's just maybe a little trickier because we've got 3's there, but not too bad. We'll get 3t times 3t, which is 9t squared. And then these middle terms, let's see, what is that? 3t times 5, again, that's 15t, and in the middle we get a negative 15t, and again, let me get out my calculator. Oh yeah, that's nothing, they cancel out, and then negative 5 times negative 5 is negative 25. The result we get is, we're going to call later, a difference of two perfect squares, and that's going to help us if we recognize that when we're factoring.
And notice that D and G, right, have different signs in the two factors, but F had the same sign. So for f, we ended up with 3 terms at the end, but for both d and g, we only ended up with 2 terms. And as Mr. Chase pointed out, I can't tell you how many times we see kids look at f and only give us 2 terms back.
Yeah.
And it's not we're not trying to just say, no, let's make this problem so hard, and we're just going to make this one always have 3 terms. We're going to get those kids, ha ha ha. No, 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 no. If you put a number in for m and multiply it times 6, subtract 5, and square it, you will not get the same result if you put that same number in for m, square it, multiply it times 36, and add 25. But you will get the same result if you plug that same m into Mr. Chase's final answer.
Yeah, and that's actually a great, like, general principle.
Yes.
Good life hack.
Yes, good
You know?
life hack.
Right?
Has
Like,
to work.
You can put remember that x and y can be numbers. These are variables, but they can take on a numerical value. So you could check any one of these algebraic identities that we've just established and check it. You know, is this right? I don't know.
I don't know. Maybe, what if p
But
was 2?
What
Would
if
it
p
work?
was 2? Yeah, see if it works. If this is the same thing as this, then maybe you got it right. Or maybe you did the arithmetic wrong too. But anyway, so math works, and that's, of course, one of the things we love about it. So I'm going to approach this h in, like, kind of in this general way. Maybe you didn't like my explanation, but too bad. We're going to do it again here because this is the same idea, even though it looks terrible, and it is a little bit terrible. If you've learned another method, feel free to use it. I like thinking about distribution. Some people use like a box or whatever, or you know, bow tie methods. All of them work wonderfully.
As long as you increase your speed in doing it.
Yeah, exactly. Anything to get the right answer in an efficient and increasingly autonomous way would be great. So we could do this a couple different ways. I mean, maybe your first inclination would be to multiply this by each term. So that would be an okay way to do it. Yeah, we'll do it that way. That is, we're multiplying this whole guy by each term. But think about maybe another way you could do it. That's a 2x minus
And again, we're
3
hoping
for
that
the
this is
record.
actually happening in your head rather than having to take the time to write it out.
Yeah, right. Like, I think maybe you could just skip to this step that we're about to write. What do we get? 6x squared. I'm distributing from the right now. Minus 9x squared plus 2x squared minus 3x minus 2x plus 3. All right, and then all we need to do now is combine like terms. I have an error somewhere, don't I? There it is. So we have 6x cubed, only one of those. We got some x squareds here, that's minus 7x squared, and then minus 5x if we combine these two terms, and then plus 3. So that's a great way to do it, although there are lots of other ways to do it. In fact, you can even, like I said, some people do like this box method, and you know, you're still coming out of Algebra 1. If that helps you to
Absolutely.
do it that way, what is it, 2x and a minus 3, 3x squared, x, and negative 1, and then you form all of the products. Notice that when we first did this, we had 6 things, 1, 2, 3, 4, 5, 6, and this is maybe a nice way to ensure that you have every combination of products from the first set of parentheses and the second set of parentheses, which is really what FOIL does too. It's just a kind of shorthand for remembering every single product you can think of, all 4 different combinations. Another way people do it too, I won't show that work in the box method, but another way people do it is just like you might have done when you were learning to multiply. Ready, go. And you multiply negative 3 by all of these things, and then you multiply 2x by all of these things, and you will, in fact, get the same answer. So there are lots of ways to do it. Whatever helps you do it is great, but as Ms. Getz said, we do want to move toward efficiency and correctness.
And the reason that is because as math is a graduating process, right? So as you graduate through Algebra 2 to Pre-Cal, if you have to make a box every time you have to do the very, very beginning of the problem, you're never going to finish your Pre-Cal problem or your calculus problem. So that's why, as you're learning it, always keep in mind that, is there a way I could do this more efficiently? How could I go backwards from this problem? Because you know that's going to happen to you at some point. So we're still on 32. They want us to completely simplify each of the following. They want us to simplify anything that is radical, which for me on this slide, there are no radicals. That's going to happen on the next slide. So I'm going to start with A, and this is again just some multiplication, realizing some of my exponent rules, that if you see the same base twice with multiplication in between, write the base once and add the exponents. And again, the reason this is because z times z, which is z squared, times z times z times z times z, which is z to the fourth, is shockingly 1, 2, 3, 4, 5, 6.
This is so boring.
I know.
I'm falling asleep.
My bad, my bad. Oh, he's the worst student, isn't he? I don't, well, you know what I'm going to do? I'm going to make
All
one of
those
your
Z's
nines.
on
Does
them.
anybody else agree with me? Mr. Chase's nines look weird.
I know.
So
Put all those
division.
Z's on the board. I was thinking.
Oh, that's, oh, I
Making me go to
missed
sleep.
that joke.
Come on.
I missed that. Oh, I'm good. This is X's. So I'm going to do this in a horrible way, which is I have 15 freaking X's in the numerator. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Over how many? 1, 2, 3, 4, 5. Gee, what happens when you divide x by x? It's 1. X by x, it's 1. X by x by 1. X by x, it's 1. X by x is 1. What is 1 times 1 times 1 times 1 times 1 times all of this? Shockingly, is x to the 10th, which I would have gotten if I had realized that if I see the same base twice with division in between, write the base once and subtract the exponents.
Preach it, Miss Getz.
Preach it! Now in K, what's the difference here? K is I do not have the same base. I have base 11 and I have base x. This is where I think see multiple bases with one exponent distribute. And shockingly, a lot of times what kids do here is they leave off the 11. They're all good with I will often get an answer like this to this problem. Right? Well, don't be hating on 11. 11 deserves the square as well. And 11 squared is 121 x squared. I guess I should box my answers, right?
The other mistake I sometimes see is people like think, oh, multiply powers. Like on the next one, you're going to be multiplying powers, and so therefore multiply. You get like 22x squared as an answer to.
Oh, right. They'll multiply the 11 times the 2. Yes, I've seen that as
Something
well.
like that.
So again, I always see the base once, one base, right? Here I had two bases, but they were different, but it's the same procedure. I'm going to distribute. I'm going to say this is multiply. This is s to the 6th. And again, I can certainly, especially in this one, I can tell you that, what does it mean to square? Well, it means you have s cubed times s cubed. But what is s cubed? SSS times SSS. Gee, guess how many s's you have? 6. So this is a combo here. First, I'm going to look inside and see if there's anything I can do inside. Aunt Sally taught me I could do that. I can just cover up this 3 here, pretend it's not there, and look at that fraction inside the parentheses and think, is there any simplification I can do? And there doesn't happen to be any this time. So now I'm going to make sure to be fair to everybody and give everybody that power of 3. So that is 2. Now this technically has a 1 with it, right? So 3 times 1 is 3. Y to the 3 times 3 is 9. 3 to the, again, that has an exponent of 1. 3 times 1 is 3. X to the 3 times 2, which is 6. And then I will expand, since this doesn't take too much brain power. 2 cubed is 8. Y to the 9th. Over 3 cubed is not 9. It is 27. X to the 6th. Now if I notice an n, I've got no exponents outside the parentheses. Nothing is going on outside the parentheses. So I can just Aunt Sally this and forget all about exponents. So inside parentheses there was nothing to do. Exponents on the outside there was nothing to do. So now I just take care of multiplying like terms. 5 times 3, again on Wednesdays, is 15. X squared times x to the first. So if I think that in my head, x squared, I'm sorry, x to the 4th, times x to the 4th, see the base twice, multiplication in between, write the base once, and add. Y to the 4th times y cubed, see the base twice, the multiplication in between, write the base once, and multiply your exponents.
All right, now we get to simplify some radicals here. So unfortunately, simplify I think is a little bit of a loaded word because
Agreed.
root 50 is pretty simple in my mind. And
I like it just fine.
so we should say, does it actually say do not write as a decimal? Okay. So we definitely don't want to write whatever root 50 is, which
But maybe
is
just
7.
rewrite instead of simplify. Rewrite it in another way.
Yeah,
Because you never know when root 50 might be just fine, but another version might be just fine too.
Yeah, exactly. But we would like to start thinking about maybe the fact that we can at least do the
Yes.
following. There's a property of radicals that we need to apply here, and that's that the square root of AB is equal to the square root of A times the square root of B for positive A and B. So that is to say, if you can recognize this as being 25 times 2 under this
Meaning
radical.
you factored 50.
Yeah, exactly.
Factoring comes up everywhere.
And you might that like recognition part is maybe the first step here in recognize. How did you know to do that, Mr. Chase? Is the question. Well, we'll maybe say some more about that because it is sometimes a little tricky. This one's obvious to me, and hopefully it'll become obvious to you. That's the square root of 25 then times the square root of 2 by this property up here that we love. And actually, we won't say anything. It should remind you a little bit, though, of some of our exponent properties that we were just looking at.
Yeah.
Root 25 then has a better name, and we can write it that way. And so for us, that's what we're going to mean by simplify. Even though, again, that is loaded, and I don't disagree if you're like, that's not simpler, because you're
Agreed.
kind of right.
But do take a moment, if you have your calculator, type in the square root of
Yeah.
50, which is not an integer, right? It
It's
is
7
an
point
irrational number,
something.
7
Hopefully
point
you
something.
recognize that.
And then type in 5 times square root of 2, and you're going to get the same answer. Those two things are equal. They're just different representations of one another.
This one. Don't think too hard about this. Okay, how can we do this? Break it up into two radicals. Root 50 times root. No, wait, hold up. This is just 10. Okay, moving smartly along. Over here, can we break up root 32? Okay, so let's go back and think about my thought process on this one. What was I looking for? I kind of just pulled a fast one on you a little bit. I was like, well, it's 25 and 2, but why didn't I say
10 times 5.
10 times 5 would be a great way to break it up too, right, Mr. Chase? Well, I'm really looking for perfect squares so that this next trick, look forward here, so that this next trick works out for me. So that's, I think, the thing we want to look for. What can we think of? Let's see. 1 always works, but it's not helpful. 4 would be great. But let's think bigger. Can we go bigger? What about 9 is the next perfect square I know? No, that doesn't work. What about 16? Does 16 go into 32? I think I'm liking 16, and I don't think I can go any bigger. But maybe I can break that into root 16 times root 2. That's 4 root 2. If that's, by the way, if you had mistakenly been like, you got so excited about the root 4 that you were like, sweet, and you decided to go for that. This is actually also the same thing.
Same thing.
But it wouldn't actually kill you if you did that, because you could then simplify the root 8, and maybe would we get the same result? Let's see how this works if we had done it that way. Hopefully we'll get the same thing. Root 8 can still be simplified. There's another 4 that can be pulled out. That's root 4 times root 2. That's 2 times 2 times root 2. So all is not lost. So this is the same thing. If you were to do it that way, full credit. It's just,
Took you one more step.
Took you a few more steps. But
And go thank your elementary school teacher, math teacher, hopefully, or your elementary school teacher that taught you math, that drilled you in your multiplication tables and your perfect squares.
yeah.
Because that's what speeds this process up. When you look at 50, you didn't, and you thought perfect square, very quickly your brain went to 25. You looked at 100, very quickly your brain went to 10. And the reason that happens, you were not born with that skill. That skill was taught to you, and you were exposed to multiplication tables, multiplying forwards, look at these squares, what happens when you multiply the same number times itself, and hopefully you were quizzed and drilled on this stuff, because it does make your life easier now.
Yeah. Yeah, and if it does help
Your math life easier.
If it does help you to completely factor the number under the radical, that is completely okay too. Sometimes these are, I think, not bad, but sometimes you do have to really think hard about the factorization. That is the prime factorization. For 32, it's 2 times 2 times 2 times 2 times 2. Okay, so can we do anything down here? I mean, the 3 makes life a little more interesting, but not very much. I want you to proceed with the root 20 the same way we've been doing. Again, can we think of a nice perfect square that goes into 20? 4 is the first one I'm thinking of, right? The smallest one. That does go into 20, and I don't think you can go bigger, so we'll just go with that. In fact, we know we can't, because root 5 is prime. I mean, that's 5 is prime. So that's 3 times 2 times root 5. And this is, again, how we want you to write it, even though that's maybe not simple in your mind. It's not much better than it was before, but that's
A
what we're
common
going to do.
mistake I see with kids here is they realize that 3 has nothing to do with their simplification of the radical, so they'll just kind of drop it off
Oh, and
altogether.
forget
Just
about it.
leave-
Yeah.
Just forget about it and leave the answer as 2 root 5. So don't forget that it is there. I like how Mr. Chase carried it down all through his work. And just,
Yeah.
again, do that mentally.
Yeah, I'm a big fan of like writing equals after each step and making sure that every step really is in fact equal to the previous step. I guess another mistake someone might make is thinking that's a cube root when it's not. That's a big 3. All right, typography 101. All right. Well, what's going on here? Okay, so one way to do this one would be to use this property and run it in reverse and be like, okay, well, 14 times 7 is 80 something. What is that?
Yeah.
90, no.
98?
98? All right, and then you could proceed with this process. But like, I had to think really hard about the root 98. Maybe we can come up with a slightly more efficient way. I know we didn't break these into perfect squares. I know we didn't break these into things other than perfect squares earlier. You might look at root 14 and you might be like, I can't break that into perfect squares. But maybe let's, just for fun, break it into root 2 and root 7. I don't know, just for fun.
Whoa, look what happened.
Now, root 7 times root 7, that's, if you wanted, you could say that's root 49 if you combined it. Or you could just think, well, what is the square root of a number times the square root of a number? That's the same, that's the number. So root 7 times root 7. Can you convince yourself that that's just 7? If so, then we're going to write 7 root 2. Is it okay if I put that out front? Traditionally, we write the thing that's not under the radical out front, and that's only just to avoid confusion. There's nothing mathematically wrong with maybe writing root 2 7. But
Some people might think, is the 7 under the radical
Right,
or is it
yeah.
out? And if it's in front, it's clearly out.
yeah, if you were to, like, what is that? Like, hopefully that is an offense to your mathematical and typographic sensibilities. Okay. And then over here, we've got some work to do. There's another property that's really the same property. Root A over B is the same as root A over root B.
Even B isn't 0.
Yeah. So again, yeah, for positive A's and B's too. Let's see. So we can maybe apply that property here.
And again, first sketch it, take a glance at the fraction to see,
That's
can
true.
can it be reduced first?
Absolutely, yeah.
Again, that's just Aunt Sally, right? Look inside the operator, which is the square root, and say, reduce your fraction.
Yeah, I didn't even think about it, but because it can't
Yes.
be. But obviously you want to think about that first. A good example of that would be like if you had square root of 8 over 2 or something like that.
Right.
For goodness sake, please let's write that as root 4 and then write 2 or something. All right. So anyway, so use this property. Just apply it right away. You get root 25. That has a better name. It's 5, and then root 32. Now,
Hey,
isn't that convenient? Let's not go through the work. We just did it right here. It's 4 root 2 over 5.
and then double check to make sure the 4, those two integers, can't be reduced, right? You would never go
Right.
up inside a radical to reduce, but the 4, for instance, if that 4 was actually a 10, the 10 over 5 would reduce to a 2.
Yeah, and so I think we've come to the end of section 32. We'll pick up with 33 in section 5 when we finish this video series. And
Thanks for hanging with us. I hope we've given you some good tips along the way, and we can't wait to see you next year.
we love you.
Bye.